everybody, it's Mrs. Dunn again. In this video, we're going to be using the TI-84 Plus graphing calculator and the normal CDF function, and we're going to be using the central limit theorem to find probabilities. So when exactly do we use the central limit theorem? So we use the central limit theorem to find the probability of a mean from a group, as opposed to the mean of one specific selection. So for example, in the previous videos where we were finding finding probabilities from standard normal distributions, normally we were finding the probability of one specific event. Here we're saying, okay, we're going to take a group of individuals. What's the probability that this group of individuals has, that the mean of that group is going to be a specific value? Now, in order to use the central limit theorem, we need to make sure that that population is normally distributed. If the population is normally distributed, then we can use the central limit theorem as long as we are finding the probability of more than one, like 2 or 3 or 4 or a group of whatever size. If the population is not normally distributed, then we must only use the central limit theorem if we are taking a sample that is bigger than 30. So how do I use the calculator? So what we're going to do is, since we are going to be talking about a normally distributed function, we're going to be using the normal CDF function again. But there's one big difference when we're using the central limit theorem. We need to adjust the standard deviation slightly. So the standard deviation is going to be the population standard deviation divided by the square root of the sample. So you should be quite used to using this normal CDF function. So the syntax looks very similar, where we have the lower bound, the upper bound, the mean, but notice we're going to be using the standard deviation divided by the square root of the sample size for our where the standard deviation would normally be. So let's look at an example. Once again, let's talk about IQ scores, because IQ scores of adults are normally distributed with a mean of 100 and a standard deviation of 15. So let's consider two different questions. The first question is, if a person is selected at random, find the probability that their IQ score is greater than 118. Compare that to if 9 people are selected at random, find the probability that they have IQs with a mean that is greater than 118. Do you see what's different about these? In the first question, we want to know what's the probability that one person selected at random has an IQ of 118. But in the second example, we want to find the probability that the mean of 9 people, their IQ is greater than 118. So let's look at the first question. The first question we've done before. Find the probability that the IQ score of one person selected at random is greater than 118. So I'll use my graphing calculator in the normal CDF function. The lower bound, remember we want them to be greater than 118, so the lower bound is 118. The upper bound is positive infinity. We're going to use 99,999. The mean is 100. And the standard deviation is 15. And the probability of this is 0.1151 approximately. All right, now let's look at question number 2. Now, question number 2 says that we're going to take 9 people selected at random and find the probability that they have IQs with a mean that is greater than 118. Notice that we were told in the problem that the IQ scores of adults are normally distributed. Because they are normally distributed and we have a sample that's of 9 people, even though 9 is less than 30, we're okay because it's normally distributed. So the only difference here is since the IQ scores, since we're looking at a group of 9 people, we are going to have to adjust this standard deviation. So we're going to take the standard deviation of the population and divide it by the square root of, oops, sorry about that, by the square root of the sample size. The sample size is 9, so the square root of 9 is 3. 15 divided by 3 is 5. This number should be a 5. Okay, so I changed it to a 5 because it should have been a 5. Okay, so moving on. When we're using our calculator to do this, we're going to go to second vars, normal CDF. The lower bound is 118. The upper bound is 99,999. Mean is 100. Now this time, in place of the standard deviation of 15, what we're going to put in here is 5. That's the adjusted standard deviation. And notice that changed the probability. This probability, it says 1.5914, etc., e to the negative 4. That means times 10 to the negative 4 power. So essentially that's 0.0002. See, because we're going to move the decimal point 4 places to the left. So it's about 0.00002. So take a look at that. Notice that the probability that 9 people, if we just randomly select 9 people and we take note of their IQ scores, the probability that the mean of those 9 adults is going to be greater than 118 is very, very low. The probability is actually less than 0.05, so it's considered to be a very unlikely occurrence. So a couple things I want to point out. Because the sample size was normally distributed, we were allowed to use the central limit theorem, even though the sample size was less than 30, because the sample was normally distributed. All right, good luck.